Hi there. Today we're going to talk about nuclear fission and fusion. This is Phychem 3 of Unit 9. We've got three key ideas. What holds nuclei of atoms together? What is released when the nucleus of a heavy atom is split? What happens when the nuclei of small atoms are joined? So looking at this first question, what's holding these nuclei together? So the stability of a nucleus depends on nuclear forces that hold the nucleus together. These forces act between the protons and the neutrons. Nuclei are held together by special forces. These special forces are referred to as the strong nuclear force. So this causes protons and neutrons in the nucleus to attract each other. And we can also say that attraction is much stronger than the electronic repulsion between the protons. Protons don't like to be too close together, but they are still more attracted to each other than they want to repulse. And neutrons help for this to take place. They're going to contribute to this nuclear stability because they don't have a charge. So they act kind of like a buffer or an insulator between those protons so they are not completely repelling each other. However, when we have too many neutrons or protons, this can cause the nucleus to become unstable and decay. Typically, those elements or those nuclei that have more than 83 protons are going to be unstable. This kind of visual to show, yes, we're all attracted to each other because of this nuclear force, but then we've got electronic repulsion between the protons. So this nuclear force is going to be stronger than this repulsion. Alright, nuclear fission. What is released when the nucleus of heavy atoms are split? In the fission process, the nucleus splits, both neutrons and energy are released. So we can define fission as the process by which a nucleus splits into two or more fragments and releases neutrons and energy. So if we take uranium-235 as an example, it's going to undergo fission by producing different pairs of lighter nuclei. So uranium-235 is hit by a neutron, and it breaks down into barium-140 and krypton-93, and then we do have some leftover neutrons as well. So we have 3 leftover neutrons, and then we get some energy in that mix also. So this energy released during nuclear fission, we can call the equivalence of mass and energy observed in nature, explained by the special theory of relativity, often credited to Einstein. So mass-energy equation is what we refer to it as. So energy is equal to mass times the speed of light squared, or, as you might be more familiar with it, E equals mc squared. So energy is released when these new nuclei form. We have something called mass defect. This is the difference in the total measured mass of a nucleus and the sum of the individual masses of the neutrons and protons that make up the nucleus. The small amount of mass changes into energy. Neutrons that are released by fission can start a chain reaction. We can call this the nuclear chain reaction. It's a continuous series of nuclear fission reactions. Chain reactions can be controlled. So if the amount of fissionable substance is less than the critical mass, chain reaction will not continue. And then a critical mass is the minimum mass of fissionable isotope that is able to provide the number of neutrons needed to sustain a chain reaction. So we looked at this equation earlier. This neutron's coming in, hitting this uranium-235, breaking it apart or splitting it, fissioning it into krypton and barium. And then the neutrons that are released hit more uranium-235, and more krypton and barium are released, and more neutrons are released, and it hits more uranium-235. So this is what we're talking about with a chain reaction. One reaction produces more possible reactions. Next thing we have is nuclear fusion. So what happens when nuclei of small atoms are joined? Energy can be obtained when very light nuclei are combined to form heavier nuclei. Fusion is the process in which a light nuclei combine at extremely high temperatures. This forms heavy nuclei, and it also releases energy. So fusion is the combining or fusing of two things. In stars, such as our own sun, energy is produced when hydrogen nuclei combine. Large amount of energy is needed to start a fusion reaction. So 4 hydrogen atoms can combine to make helium atoms and high energy gamma rays in a 3-step process. So 2 hydrogen 1s combined forms hydrogen 2 plus some other particles. Taking that hydrogen 2, combining another hydrogen 1, we get a helium 3 plus some gamma radiation. And then this helium 3 reacting with another helium 3 from another set of reactions produces our stable helium 4 nucleus plus 2 more hydrogen 1. So here's just a visual of what's going on. 2 hydrogen, some particles, hydrogen 2 and hydrogen 1, and then we get helium 3 that's produced. 2 helium 3s react, produce helium 4, and then 2 more hydrogens. Thanks for listening.